Okay. Hello everyone. So this is the 10th week. We are meeting for the course Fluid and Particle Mechanics. So in this week, I will mostly solve the assignment problems. Okay, related to turbulent flow, and if I get time, I will also solve the problems related to friction factor, head loss, and all these things. That is the minor losses and the major losses. Uh, okay, so let me directly go to the assignment 9, I guess. Yeah. So let me solve from problem number 1. So what it says is that, so this is problem number 1. Okay, so it says that ammonia at 20 degrees Celsius flows through a pipe at 0.01 meter cube per second. So what is the flow rate? Q is equal to 0.01 meter cube second inverse, and a frictional head loss of 12.95 meter. That is the head loss due to friction. HF is equal to 12.95 meter. The power required to drive this flow. Okay, so what is frictional head loss, by the way? So the frictional head loss can be represented in terms of so the screen friction coefficient, if I calculate the screen friction coefficient, CF is equal to screen friction coefficient, or the fanning friction coefficient, whatever you will say. Let me do that for your benefit. Yeah, so the skin friction coefficient, let me write it down. CF is equal to the wall shear stress divided by half rho v square, where this tau w is the wall shear stress and rho v square is the screen friction coefficient. Okay, so tau w is the wall shear stress and rho is the density of the fluid, and v is the average velocity of the fluid. Okay, so this is the screen friction coefficient. Now there are two different types of screen friction coefficient. Okay, one is the fanning friction coefficient. Fanning, we will also represent it by CF. This is equals to 1 by 4 into dH by L. I will tell what is these individual terms are, into pressure drop delta P divided by half rho v square. Okay, so this dH is the hydraulic diameter. Okay, which is equal to 4A by P. Okay, where this A is the cross sectional area of the flow. A is the cross sectional area of the flow, and P is the perimeter of the section. Okay, and L is the length of the channel or the pipe. If it's a pipe flow, if it's a channel flow, L is the length, delta P is the pressure drop. So this is the fanning friction coefficient, and I have another friction coefficient which is Darcy's friction factor, which will represent by F is simply equal to dH by L into delta P by half rho V square is equal to 4 into fanning friction factor. Okay, so what is pressure drop? So pressure drop delta P can be written as, so what is delta P? Delta P is equal to F, that is the friction factor, into L by dH into half rho V square. Okay, so what is the head loss? This is the pressure drop. So what is the head loss due to pressure drop? So the head loss due to pressure drop, so the head loss if I write it as H L, or that's ultimately due to friction, so HF will be equal to delta P divided by rho into G, so that is F into L by dH into V square by 2G. Okay, for pipe flow, dH equal to D is the diameter of the pipe, and you can easily get that CF is equals to 16 by RE. Okay, and F is equal to 64 by RE, that is the friction factor, where RE is equal to rho V D by mu is the Reynolds number. Okay, so in case of laminar flow, so in case of laminar flow, F is a function of RE only. Okay, in case of turbulent flow, in case of turbulent flow, F is a function of both RE and epsilon by D, where epsilon by D is the a relative surface roughness, because the any surface will always have some roughness, where epsilon is the roughness height and epsilon is the average roughness height and D is the diameter of the pipe. Okay, and epsilon by D is the relative surface roughness. And in Moody's diagram, actually you can plot this friction factor versus RE in the laminar zone and in the turbulent zone, and in the turbulent zone it is the function of epsilon by D as well. So I am not going into the details of that thing. Okay, So what was the question? The question was that you have a head loss is given. Okay, so HF is given and you are asked to find out what is the uh, power required to drive the flow. Am I right? So the power required to drive the flow. So the power required to drive the flow, okay, is equal to what? Power required will be, so you will have a pressure drop, okay, and to overcome that, to have that pressure drop or to overcome the friction, there will be some pressure drop and thus you require power, and that power required will be rho g HL HF rho g q into HL. Am I right? So this will be the power required. So what is this? So this is, so what is the value of rho? So okay, the value of rho is not given, so I'll just write it as rho. This is equal to 9.81 into Q is equal to 0.01 into HF equals to 12.95. So what is this as coming? So this is 9.81 into 0.01 into 12.95. So this is coming as 1.2704 into rho. So the rho is not given in the problem. So I think the density of ammonia, I think it will be at 20 degrees Celsius it will be gas, I guess. At minus 20 degrees Celsius it will be the density of ammonia at minus 20 degrees Celsius. So let's say rho is equals to something around 600 kg meter cube. The power is equals to 1.2704 into 600. How much is that? Is equals to 762 watt. Anyway, so that's depends on the density you are choosing. I choose as 600 because I think it will be minus 20 degrees Celsius. Anyway, so let's move on to the second problem. So you got the point, right? So that's the important, not the numerical value. Okay. So second problem says that benzene at 20 degrees Celsius is to be transported through a 0 point, so L equal to 0.5 meter. So benzene at 20 degrees Celsius is to be transported through a 0.5 meter long smooth, there is no roughness, and D is equal to 20 centimeter, means 0.2 meter diameter. It is desirable to obtain maximum flow rate but maintaining laminar flow conditions. Okay, maximum flow rate but maintaining. So what will be the flow rate? Q is equals to pi by 4 d square into average velocity v. So you want to maintain the maximum flow rate, but at the same time, let's say RED equals to rho Vd by Q, sorry, rho Vd by mu. So the laminar pipe flow, that critical Reynolds number below which the flow is always laminar is, let's say, 2300. Okay, without moving laminar flow conditions, without moving to transition or turbulent flow, the maximum pressure drop for which the flow will be, the maximum pressure drop for which the flow will be the flow can be obtained is how many pascals. So what is the friction factor? F. So friction factor F is equals to 64 by RED. Okay, 64 by 2300, this is the friction factor, and delta P is equals to F into L by D, L and D both are given, into half rho V square. So in order to obtain the maximum velocity, maximum flow rate, the D you can't change, so you can only increase the velocity. Okay, so from the Reynolds number, so V, now V is equal to mu into RED divided by rho into D. Am I right? Yeah, that is V. So V should be maximum because rho D mu you can't change, and RED, which is the critical Reynolds number, 2300. Okay, what is the value of delta P? Delta P, so F is equals to 64 by RED into L by D, okay, into L by D into half rho V is equals to mu RED divided by rho into D square. Is that fine? Half rho V square. Okay. So I know the values of L, D, RED. That's all right. So once I know the value of rho and mu, what was the liquid? The liquid was benzene at 20 degrees Celsius. So I request you to put the values of take the values of appropriate values of mu and rho to calculate delta P. I will not go into the details calculation of that. Okay, so this is how you can calculate the pressure drop. Fine, let me go to the next problem, problem number 3. What it says, so water is flowing in a pipe at, so you have given the flow rate Q is equal to 1 meter cube per hour. So that means, so 1 by 3600 meter cube second inverse, that is the Q. So water is flowing in a pipe at 1 meter cube per hour between point A and B. A mercury nanometer connected between these 2 points gives a reading. So the difference between the heights, so it gives a reading of that thing. That means what is the pressure drop? Pressure drop is the rho m, density of the mercury, G, into the reading of the manometer. Let's say that is hm. Okay, reading of the manometer, that will be the delta P. So pressure drop is given. Okay, so what is rho m? I think rho m is equal to 13.6 into 10 cube kg meter to the power minus 3. hm is also given as 35 millimeter, is equal to 35 into 10 raised to minus 3 meter. Okay, that is the hm, and G is equal to this. G is equal to 9.81 meter per second square. Okay, so now from here you can calculate what is delta P. Anyway, the pipe is 1 centimeter in diameter, while the length of the pipe between point A, so diameter of the pipe is 1 centimeter. Fair enough. That is 0.01 meter. That is the diameter of the pipe, while the length of the pipe between point A and point B is equal to 50 centimeters. 0.5 meter. However, the pipe is not horizontal, but rather the point B is 30 centimeters. So let me draw it. So if let's say this is my pipe, where I will have a manometer connected. Okay, and at some point I have a manometer connected. Okay, so this is section 1, this is section 2, so this is point section A, section B, let's say. So the height of this is 30 centimeters. Okay, 30 centimeter below. Okay, so that means this is my point A and this is my point B. Okay, and from A to B there is a mercury manometer connected between these 2 points, gives a reading of 35 millimeter. Fine. Okay, it is given that the pressure at point A, PA, here the pressure is, let's say, PA, and here the pressure is PB. It is given that pressure at point A is greater than pressure at point B, is higher than the point B. Assume room temperature. Fine. So let me see this. So I have given the flow rate, I have given the pressure drop in terms of the reading of the manometer. So okay, and then I have given the diameter of the pipe. Let's say this is the diameter of the pipe, D, and the length of the pipe is also given between point A and point B. I have given the length of the pipe. This is L. Fine. What I have asked. Okay, so point B is 30 centimeter below point A, and then PA is greater than PB. Okay, then the first question, the direction of the flow is from, so the diameter is not changing, diameter is fixed, pressure at point A is more than pressure at point B, also the point B is at a lower height. Okay, so definitely the flow will be from point A to point B. You can also apply the average velocity will be around. Okay, so let us calculate the average velocity. So what will be the average velocity? So the flow will be definitely from point A to point B, because there is a pressure at point A is more than the pressure at point B, and also point B is at a lower height than the point A. That means definitely the flow will be from point A to point B. Okay, also you can calculate the sum of all the heads, pressure head, velocity head, and the potential head at point A and point B, and you can easily say that the head at point A is more than the head at point B. That's why the flow will be from higher head to lower head, or from the higher energy to the lower energy. So that will be from the A to B. So this is the direction of the flow. Fine, from A to B is the direction of the flow. Now they asked to calculate the average velocity in the pipe. Okay, so the average velocity V, flow rate divided by the area, 4 pi d square. What is the flow rate? 1 by 3600 divided by pi by 4 into what is the value of D? D is given as 1 centimeter in diameter, 0.01 square. So how much will be this? So this will be okay, so I am getting it is 3.536. So I am getting it as 3.536 meter second inverse, as you can see. So that is what which I am getting as the average velocity. Okay, that is Q by Q divided by cross sectional area, that is pi by 4 d square, that is the average velocity. Okay, now what is the next question they are asking? The manometer reading will be proportional to head loss, inversely proportional to head loss, will be a constant, will be proportional to square of the head loss, will be inversely proportional to the, of course the manometer will read the head loss, the pressure drop. Okay, the manometer will definitely read the head loss, will be proportional to the head loss actually. What is the next question? The Reynolds number describing the flow. The Reynolds number. Okay, so based on that I can say that whether the flow is a laminar flow or a turbulent flow. Am I right? So So let me calculate the Reynolds number. Based on the diameter, RED is equals to rho VD divided by mu. Okay, so what is rho for water? 1000 10 cube kg per meter cube. What is the velocity? 3.536 is the velocity. What is the diameter? Is 0.01. Fine. Divided by so rho VD by mu, and mu is around so it will be, so what is the dynamic viscosity of water? Let me see it. Okay, so it is around 1.0016 into 10 raised to minus 3 Pascal second. Okay, so that is the viscosity of the water, and the density is 1000. So what is the Reynolds number in this case? So let me calculate the Reynolds number. So how much is this coming? 10 raised to 6 3.536 into 0.01. So it is something around 35,000. Yeah. What is the Reynolds number? So Reynolds number is coming something around 35,303.5. So this is the Reynolds number of the flow. Okay, so the Reynolds number describing the flow is this. If the flow is assumed to be laminar, okay, imagine you are in a world of zero disturbances and you have automatically smooth pipe, that flow can remain laminar for any Reynolds number, for example. Then the friction factor can be calculated as, so what will be the friction factor in case of laminar flow? So the friction factor for laminar flow, AP is equal to 64 divided by RED. So how much is this? So that is equal to 64 divided by 35,303.5. What is that? So this is, so it is 64 by RE as I wrote, into 64. It is coming as 0.0018. Yeah, it is coming as 0.0018 13, something around that. Okay, so first I calculated the average velocity, that is 3.536. Then I calculated the Reynolds number, then I calculated the friction factor. Okay, the pressure drop across A and B. What will be the pressure drop across A and B? So the manometer has a reading of this. So let me calculate the manometer reading in terms of the pressure drop. Okay, so rho m g into hm. What is this? So this is 3.6 into 10 cube is the density. G is the 9.81. That's what I wrote, into 35 into 10 raised to minus 3 into 35 into 10 raised to minus 3. That is the manometer reading. Fine. So how much is this? So 13.6 into 9.81 into 35. So something around 6. So that too is in meter, right? Yes, 35 millimeter, right? Yeah. So this is coming as 4669.56 Pascal. Okay, so that is what the manometer reading in terms of pressure. What they are trying to say, the pressure drop across A and B. So this is what the pressure drop is across A and B. So this is delta P is equal to this. Fine. The head loss in meter. So 1 minute. So this is your pressure drop across A and B. Fine. So this is your pressure drop, and then what I have is 30 centimeter below it. Okay, so the head loss and what about the velocity head loss? I don't think there will be any velocity head loss. So if I applying the Bernoulli's equation, between section A and B, we have what we have that rho A, sorry, so this is PA, so the flow is from 1 to 2, that is PA divided by rho W water into G, that is the pressure head, plus VA square by 2G plus ZA is equal to PB divided by rho W into G, okay, plus VB square by 2G plus ZB plus head loss, let's say HL or HF, I mean the total head loss, okay, HL. So this term and this term are the same, VA equal to VB, okay. So what you have in effect is HL is equal to PA minus PB divided by rho W into G, okay, fine, plus ZA minus ZB. So I think the pressure head loss between this A and B is what is the manometer reading, okay, that is 35 millimeter. So 35 into 10 raised to minus 3, okay, plus you have the distance between the two, which is 0.3 meter. So how much is this coming? That will be the head loss. So it is 0.3 plus 0.035, so it is 0.335 meter. That's the total head loss. What is the answer here? So head loss in meter is in between 0.4 to 0.5. No, sorry, I have the pressure drop, so I'm doing a wrong calculation here. I'm extremely sorry. So that is not the manometer reading, okay, that is the difference in pressure between point A and point B. That is not exactly the manometer reading. So what we will have, what is the PA minus PB? So this is equal to PA minus PB. So this many Pascal, okay. So what I am getting ultimately is that 466.9, 469.56 divided by 10 cube is the density of water into 9.81. This is in meter plus 0.3, okay. So what is that? So 466.956 divided by 1000 into 9.81 equal to 0.47 into 0.47 plus you have that as 30 centimeter, right? So that is equal to 0.476 plus 0.3. Okay, no, but the manometer reading will give me the head loss, right? So I don't need to actually apply the Bernoulli's equation. So my head loss due to pressure will be head loss due to pressure drop. Okay, that is, I can also write it as HF HL can be this thing also, PA minus PB divided by rho W into G. That is the head loss, which is coming as 0.476 meters. Okay, so that is the head loss, because the manometer reading will be proportional to the head loss. Okay, yeah. So in head loss, I don't need to consider this part. I don't need to consider the other part. This will do the job. I guess. So that thing is actually not that important. These things will do the job. Now the last thing which is important, the friction factor. Now the actual Reynolds number is 35303.5. Okay, so the actual Reynolds number will be also different, right? So what, like the actual friction factor will also be the different. So what is the actual friction factor? Now based on the laminar condition, the friction factor is something around 0.0018. So how you will calculate the friction factor for, so let me write one thing out here. So you can see, so far we have calculated the average velocity, and then Reynolds number, and then friction factor, pressure drop, and then the head loss. Now the last part is saying that what is the actual friction factor. Now here I have not given any information about the surface roughness. Okay, so in order to calculate the actual friction factor, I have to use some formula, I guess, some empirical formula. So what are those empirical formula by which I can calculate the actual friction factor? So in case of, so let me write it down. In case of turbulent flow through smooth pipe, we have the empirical, we have the following relation for friction factor. Okay, so what is the relation? That 1 by root f is equal to 1.99 ln of RED into root f minus 1.02. So this is the relation. This actually derived in the class for the turbulent pipe flow. So I know this RED. What is the value of RED? RED is 35303.5. 35303.5. So how should I calculate the actual friction factor from here? So the actual friction factor from here can be calculated. So this is a non-linear equation. You can't directly put the formulas and calculate it. So for this you need to solve it using numerically. Okay, you need to solve it numerically. So how will you solve it numerically? Let me see if I can show you that how to solve it numerically. So let me open the Mathematica here. Yeah, so I was trying to do something before also. So you need to solve this equation ultimately. What is that? That 1 by root f minus 1.99 ln of RED into root f plus 1.02 is equal to 0. These things you can solve it using Newton-Raphson, any numerical scheme what you studied. 35303. So I'm just using an ND solve. So in Mathematica you can using the command subroutine ND solve, you can directly solve it actually. 0.5. Okay, so let me see that what will give this. This is coming as 0.0047. Is that the answer? So it is 1 by root f into minus 1.99 ln of 35305 into root f plus 1.02 is equal to 0. So how much is the, so here it is giving f is equal to 0.00475. that is how I am getting from numerics using this turbulent pipe flow friction factor equation. Okay, so this is what I am getting. What is here? Here it is given 0.02 to 0.03 friction factor. what was the friction factor here? 0.001813, 0.00475. I think this is what I am getting. So according as also I showed how to solve it numerically. Okay, anyway, so now we'll move to the next one. So the next one shows that, fine, what it says, match the following according to the given figure. So A is the boundary layer, growing boundary layer region. Definitely the A is the growing, this A where the boundary layer is developing from both the side. So this A is the growing boundary layer region. So A is Roman 1. A will match with the Roman 1. B is the inviscid core flow. So when a flow will enter through a pipe, there will be some entrance length where the boundary layer will develop, and before the flow get fully developed, these two boundary layer will merge at some point C, and then the velocity profiles will no longer change from point C onward. Okay, so the B is the inviscid core flow. C is where the boundary layer merge, because two boundary layer are developing from the two side is marching at point C. D, what is D? D is the velocity profile, developed velocity profile. So D is Roman 4. E, as I said, that E is the entrance length. Okay, up to which the entrance effect will be there, and the velocity will be not fully developed up to the entrance length. And F is the fully developed flow region. I think that should be the answer. Yeah. Okay, now let's move to the next one. This is an interesting, I think this should be also interesting somehow. Fine. What is this? Match the following according to the figure below. So this is a turbulent pipe. So this is a turbulent shear flow. Okay, so this U plus equal to Y plus is the equation for the wall layer. U plus equals to Y plus is the equation for, so first of all, before getting to the answer, so in the x-axis you have logarithmic plot, like in log spacing you have in the along the x-axis you have log scale, along the y-axis you have the linear scale. So this B is equals to y u star by nu. Okay, that is the some sort of non-dimensional length scale measuring from the y. Okay, and this D is the non-dimensional velocity scale, where u by u star is the non-dimensional velocity, where u star, as you know, that this is the friction velocity. Okay, and nu is the kinematic viscosity of the fluid. So B is, so this B is y u star by nu, and this D is u by u star. Okay, now let us see. So the C, okay, what is A? A is the overlap layer. So you have the wall layer, then the overlap layer, and then the turbulent layer. Okay, or the outer layer. So in the overlap layer, so you have the equations for the equation for the wall layer is u plus equals to y plus. Equation for the oval layer is u plus equals to 1 by k ln you have discussed this for the overlap law or the logarithmic law, that is 1 by k ln y u star by nu plus b, where k is 0.41 and b is approximately 5. So A is the overlap layer. What is B? Where is B here? Okay, B I already told. C. So C is the linear viscous sublayer. C should be the linear viscous sublayer. Okay. D I already told. D is u by u star. E is the logarithmic overlap. Okay, because that's the logarithmic scale in the overlap region. And F is the so F is the linear viscous sublayer. Okay, F is the linear viscous sublayer because that's a linear scale, and A is the inner layer. A is the overlap layer. So okay, let me do it from the beginning. A is the overlap layer. Where is B? B is y u star by nu. C is the inner layer. C is the inner layer. Am I right? Yes. D is the u by u star. E is the linear viscous sublayer. F is the logarithmic overlayer. That should be the answer. Yeah, F should be this thing, linear viscous sublayer. That's an interesting problem to have, I guess. Okay, so we solved few problems. Now let me see, I can go through any other problems here. So let me go to the problems for the 10th week. So I guess for problem 1 to 6 it should be the same sort of problems which I solved just now. Let me go from problem 7. So okay, as I said that, so here they are saying that hydraulic diameter. So let me solve the problem number 7 here. Okay, so problem number 7. What is, so a liquid is flowing, some fluid is flowing, where A and W is given, L is given. So what is the hydraulic diameter? DH is 4A by P, as I said. So what is 4? So it is 4 into A means 20 into 10, because that's the cross-sectional area, divided by 2 into 20 plus 10. So how much is that? So it is 40 into 20 divided by 2 into 30. So it is 40 by 3. 40 by 3. That is precisely 13.33 micrometer. Okay, that's the hydraulic diameter. Okay, so the next problem is, while calculating the friction factor relationship for flow through an annulus with inner and outer cylinder radii being B and A respectively, so you have flow through an annular. Okay, so this is my cross sectional area through which the flow is happening. So this is that cross sectional area, this is B and this is A. Fine. So for 4 different students obtain the following relationship. So as I said, HF should be, what is the relationship for HF is equals to length scale ratio divided by V square by 2G. So except the okay, so what should be the correct answer? That's what is the question. So without doing detailed calculation, can you tell which among them could be the correct one? So let me see how they are calculating. So F should be the dimensionless, that's what I can say. So out of that, I think the dimensionless should be the 1 as far as I can guess. Yeah, I think the student 1 is correct. Yeah. What is the expressions for the hydraulic diameter in this case? So DH, expressions for the hydraulic diameter in this case, DH is equal to 4 into pi A square minus B square is the cross sectional area through which the flow is happening, divided by 2 pi A plus 2 pi B is the total perimeter of the cross section. How much is this coming as? I think it will be 2 into A minus B. Yeah, that is what is the channel diameter, hydraulic diameter. Loss coefficient that describe the measured minor loss. Loss coefficient that describes the measured minor loss is head loss divided by velocity head divided by head loss velocity head loss minus velocity head loss divided by velocity head. Okay, loss coefficient that describe the measured minor loss is head loss divided by velocity head. Okay. Minor loss are mostly due to the sudden contraction or sudden expansion, or let's say when you have a bend, so that is the bending loss. So those are the minor losses. Okay, I will not go into the details of that, how to calculate the minor losses, the head loss, the minor losses. I will not go into that. Minor losses will also, you are asked to say whether these statements are true or false. Minor losses will always be smaller than the friction losses. Minor losses will always be smaller than the friction losses. That is not necessarily true always. So that is the false statement. Moody's chart can be used to calculate the minor losses in a piping system. No, the Moody's diagram is mainly for the friction losses. Okay, that is the major losses. So that's false. Frictional loss associated in a partially closed valve is considered as a minor loss. Yes, so when there is a valve and all, that should be a minor loss. In a sudden contraction, flow separation in the downstream pipe causes the mainstream to contract to a minimum diameter called the vena contracta. Yes, that is why the minor losses take place in because of sudden contraction. The loss coefficient of all submerged exists no matter how well round is unity. Loss coefficients of all submerged exists no matter how well rounded is unity. Yeah, that's true, I guess. The vena contracta exists whenever the piping system has a sudden expansion or a sudden contraction. Exists whenever the pipe system has a sudden expansion or a sudden contraction. That's not necessarily true, I guess. Yeah, so let me solve the one last problem. So this is a similar type of problems. I think I just had it in the previous case, so I can't solve all. So let me solve one more problems and end the class. So what is that? Question number 17. Pressure drop in a 500 millimeter diameter horizontal pipe. So T is equal to 500 millimeter. 0.5 meter is the D. Pressure drop is given delta P equal to 100 kilopascal. (10 to the power 5 Pascal) over a length of 50 meter. L is equal to 50 meter. The shear stress at the pipe wall in kilopascal. The shear stress at the pipe wall. So the wall shear stress in case of pipe flow is equal to that R by 2 into dP dz if Z is the direction of the flow. Okay, if Z is the direction of the flow, then there is a pressure gradient along the Z direction, that is dP by 2. Okay, and the wall shear stress is nothing but R by 2 minus dP dz. So what is R? So it is 0.5 divided by 2 divided by 2 is equals to 4 into you have 10 to the power 5 Pascal divided by 50 meter. So how much is that coming? So it is in terms of kilopascal, right? So it will be (50 into 10 cube divided by 50 into 4). It will be 0.25 kilopascal. How much is the answer? I don't know. Let's see. It should be 0.25 kilopascal. That should be the answer. Okay, I think this is a lot of information. I will not. So at least you got the point how to solve the problems, right? And these are the, I think, the quite trivial problem. It is not that simple but not that difficult also. You can solve it. So okay, I'll stop it here and we will meet in the next week. Thank you.